Welcome to Astronomy 103. In this module, we will look at the stars. The stars seem so far away, so how can we know anything about them? So it turns out we know a lot about them. In fact, I would argue that our understanding of the stars is the crowning achievement of 20th century astronomy. But it took 2,000 years for us to get there. So what do we need to know? So first of all, we might want to know how big they are, their mass and their size. How bright do they shine? And how do they shine? We sort of know this already from a discussion of the star nearest us, the sun. So to tackle this, we must first know how far away they are. So how do you measure the distances to the stars? So there are various methods of doing so, right? But the first method is a geometric method called stellar parallax. So for the very closest stars, you can measure you can measure how much they shift against more distant stars over a course of 6 months. So why 6 months? 6 months is the time it takes basically for the Earth to move from one side of its orbit to the other side of the orbit. So the distance between where you were in January and where you are in July is 2 AU, because the average is 1 AU from the sun, so times 2. Okay, and if a star is close, what will happen is that star will appear to move relative to the background stars between January and July. So this tiny shift, right, can tell you about this is that star. This shift is very tiny. In fact, it's so tiny that no one saw until 1838. The shift is about basically 1/360,000 of a degree, or about 1 arcsecond. Right? So for instance, the shift depends on basically how far away the star is. So for a nearby star, the shift will be one thing. For a very close star, it will be a much bigger angle. So this might be one angle here. This angle here will be much, much bigger, right? So the larger shift, the closer the star. But there's a limit to how well you can do this for stars. And so basically this limits this technique to only the closest stars. Right, so for instance, if you look at this image right here, there's a star now. Star is 6 months from now. Look at this, move slightly relative to a background more distant stars, which barely shift. Okay, so the parallax angle P of a star is the angle formed by the star and the radius of the Earth's orbit. Right, so that's basically the radius of the Earth's orbit. Okay, this apparent shift in star position is due to the Earth's motion around the sun. So when the angle is about 1 arcsecond, the star's distance is about basically 210,000 AU, or 3.6 light years. So this distance is a natural unit, all right? And this is called 1 parsec, or 1 parallax second, or PC for short. So basically 1 parsec is 3.26 light years, or more simply, about 3 times 10 to the 13 kilometers. Okay, so that's the first technique. Okay, so you can basically measure the distances to the few of the closest stars, right? But there's another way of doing it. It's called spectroscopic parallax, right? We'll talk about how this works in a second. But the basic idea is the following: if you know how bright it is, you can tell how far away it is by looking at how bright it's seen. Right. So, for instance, this is a train. Okay, the train has a certain light in the front, given a known power. Right. If it's far away from you, it appears bright as if basically it's very, very close to you. Right. So how bright something seems depends on the distance. So this is how bright it seems. The apparent brightness is equal to the luminosity, how bright it actually is, divided by how far away it is, r squared. Right. Okay. So basically, some problems that we will be using will be based on the fact that apparent brightness is proportional to 1 over the distance squared, right? So there's a very good reason for this, right? As light moves away from the star, right, its energy is spread over a larger area. So that area is proportional to the distance squared. And so that's why the light drops off as 1 over distance squared. Okay. So the brightness at one region at a certain distance is equal to the brightness at the other region divided by that distance squared. So the brightness is proportional to 1 over d squared. Okay, so here's an example, right? The brightness of sunlight on the Earth is 1400 watts per meter square. The distance from Earth to Sun is 1 AU. What's the brightness of the sunlight at Saturn? 10 AU from the Sun. Well, let's go ahead and do this. Okay, so we'll just do that first. Okay, so let's go to our little paper here. Okay, so we know that basically the current brightness, so Earth brightness from the Sun, 1400 watts per meter squared. Okay. All right, and we know that the distance is equal to 1 AU. Whoops, 1 AU. Okay, so then what is that Saturn? So Saturn is at 10 AU. Right, so what is this brightness? Okay, so let's say we know the brightness of the Earth, B1, is equal to 1400 watts per meter squared. The distance of 1 is equal to 1 AU. Okay, the brightness of 2, which is Saturn, is question mark, but the distance is known. This is 10 AU. Okay, so again, that formula is B2 is equal to B1 times D1 squared divided by D2 squared. Okay, so you know everything here. This is 1400. Okay, this one is basically 1 squared divided by 10 squared. It's basically 1400 divided by 10 squared is 100. So that's basically 14 watts per meter squared. And there is our answer right there. Okay. All right. So let's go back. A few other examples here. Whoops. Let me get all the examples first. Whoops. Okay. So there we go. Okay. So the first one is what's the brightness of the sun at 40 AU if it's 1400 watts per meter squared at 1 AU? What about 100 AU? And the sun has a apparent brightness of 0.0014 watts per how far away it is, right? Okay, so let's go through each of these in turn, right? Let's move it here. Let's create my, there we go, there, and I'm gonna need to move things around so I can see it again. All right, so number one, okay, we want to know our brightness of sun. At 40 AU. Okay, so B1 we know is 1400 AU, right? Because that's the brightness of sun at Earth. D1 equals 1 AU. D2 is 40 AU. And B2 is equal to question mark, right? So B2 equals B1 D1 squared over D2 squared. Okay, so let's plug everything in. This is 1400. D1 is 1 squared divided by 40 squared. This is 1400 divided by, whoops, 1 over 40 squared is 1600. Okay, so what is this thing? This is 7/8. All right, well, actually, okay, so let's do it. So this is 14 over 16 essentially. All right, well, let's write it like that. Okay, which is, if you run that calculation through, 7/8. I know 1/8 is 1/8 is 0.125. So this is 0.875, I think, watts per meter squared. All right. Okay. Number two. Okay. What about at 100 AU? So basically, again, B1 is 1400. What's not AU right there? Watts per meter squared. D1 is equal to 1 AU. D2 is equal to 100 AU. And B2 equals question mark. All right. Okay, so let's write the equation down again. B2 equals B1 D1 squared over D2 squared. Okay, let's plug everything in. So this is 1400. Okay, this one is 1 squared divided by 100 squared. So this is 1400. This is a 1 over 10,000, right? Okay, let's go to scientific notation. 1.4 times 10 to the 3 divided by 10 to the 4. Look at that, so much easier. This is equal to 1.4 times 10 to the 3 minus 4, which is 1.4 times 10 to the minus 1, which is 0.14 watts per meter squared. Okay, so that was simple. Yep, that was simple. Okay. All right, last one, right? So number 3 is basically an inversion problem. So we know that basically B2, so parent brightness is 0.014, wait, 0.014 watts per meter squared. D2 equals question mark, right? And we know B1 again. B1 is 1400 watts per meter squared, and D1 equals 1 AU. All right. Okay, so let's do this last one. So B2 is equal to B1 D1 squared over D2 squared. Okay, so B2 was that 0.0014 is equal to 1400. D1 is 1 divided by D2 is something I don't know yet. Okay, so at this point, it's probably best to use scientific notation. So this one goes 1.4 times 10 to minus 3, because it's 1, 2, 3 decimal places over. It's equal to 1.4 times 10 to the 3, 1, 2, 3 decimal places over, 1 over d squared. Okay, so let's just change this up. So this is going to be d. So move this there, move that there. D2 squared is equal to 1.4 times 10 to the 3, 1 over 1.4 times 10 to the minus 3. So this is going to be equal to 1.4 over 1.4, thankfully, times 10 to the 3 divided by 10 to the minus 3. So this is going to be basically 1 times 10 to the 3 minus a minus 3. Minus a minus 3 is plus 3. So this is basically 10 to the 6 is d2 squared, right? So you take the square root of that, 3 AU. And that's our final answer. Okay, so let me turn off this thing here, and let's go back to our slideshow here. Okay, so this apparent brightness that we're using right now is measuring units of watts per meter squared. This is a far more rational unit of measure that is dependent that is useful for this class, right? But it relies on the fact that we know something about power and stuff like that, because there's something called watts, right? And the last time you measure watts was basically either your light bulb, or basically how fast you're running, or basically how powerful something is, right? Based a lot in large part on modern technology. But people have measuring brightnesses for way longer than that. So there's a much older scale. So invented by the Greek astronomer Hippocrates, after whom the Hippocrates satellite was named, right? So you probably remember him for the discovery of the precession of the equinoxes. So what he also did, he ranked the stars by apparent brightness, where the brightest star assigned magnitude 1 and dimmest star assigned magnitude 6. So magnitude 1 is about 100 times brighter than magnitude 6 stars as seen from Earth. Okay. So although we will use this luminosity of the star, we typically measure it, at least in this class, of sun's luminosity in watts, right? The units of magnitude are still used by astronomers and appear everywhere if you look for popular treatment of astronomy. So the only things you need to know about magnitude for this class, at least, is the inventor magnitude scale and the original range of magnitude. So magnitude 1 to magnitude 6. So here's the thing that's interesting about that. So it's unlike, it's backward from all the scales that used to. Usually larger numbers mean more brighter. Here, smaller numbers mean brighter. So for instance, magnitude 1 is brighter than magnitude 6. All right, just keep that in mind. Okay. So here's extended range of the magnitude scale, right? Okay, so each decrease in magnitude by 5, basically, so if you decrease the magnitude by 5, go to small numbers by 5, you increase the apparent brightness by 100. So the sun is basically about 10 to the 6 times brighter than the full moon, and so basically it's about each unit is 5, so 5 plus 5 plus 5, so basically 15 magnitudes brighter for 15 magnitudes lower, smaller than the magnitude for a full moon. The most sensitive telescope, Hubble and Keck, sees stars at 25 magnitudes larger, dimmer than you see in the night sky. So for instance, this, if you look at the night sky, basically the naked eye can see a magnitude 6 star. The Hubble Keck telescope can see up to 30 or 31 or so. These are the dimmest stars you could possibly see. So you know, as you get to larger magnitude, you go dimmer and dimmer. Okay, and basically, if you go the opposite way, as you get to smaller and smaller magnitude, right? So basically, this is magnitude 6 is the dimmest, faintest star you can see in the night sky. Alpha Centauri is basically at magnitude 0. Sirius, which is the brightest star we see in the night sky that is a star, is magnitude minus 1.5. Venus, which is a planet, so technically not a star, is a magnitude minus 4.4. The full moon is a magnitude minus 12.5, and the sun, brightest of all, is minus 26.7. Right. Now, it would be great if every star was like the sun. We know how bright the sun is. We can measure stars like that. But unfortunately, they are not all like the sun. So we need to know a little bit more stars if we're going to use them, use the apparent brightness that we see in order to measure their distance. So how bright are the stars intrinsically? So how bright something appears depends on two things. The first thing it depends on is how bright it is, like light per unit area that's putting out. And second thing is how big it is, right? So you see basically there are regions here, like you see the outline of the night sky of planet Earth, right? This is New York City, right? It's pretty bright. There's Chicago, pretty bright. There's London, that's pretty bright. That's Paris, also pretty bright. There's Japan, pretty bright. There's South Korea, pretty bright. That's North Korea, not much bright at all. And there's China, pretty bright. Okay, you can also see basically where people are concentrated. Australia, right? It's all along the eastern coast. Some people in the west coast in Perth, and basically no one in the middle, right? Africa as well, there's no one there in the middle as well. Siberia, you can almost see the line of towns that follow the Siberian Railroad stuff, right? And in Canada, there's nothing else, or neither is happening in Alaska. Okay, so we need to know basically how bright it is, light per unit area, and how big it is, right? So how do we do this? So we need to be able to tell how bright they are, and we need to tell how big they are. Okay, so let's remember this. Uh, the peak intensity of light emitted by a star depends on the temperature of the star, right? So the hotter it is, the more intrinsically brighter it is, right? So hotter objects have a brighter, more light per unit area, and emit at shorter wavelengths. So the key is understand what the temperature of a star is going to be, right? So we know because of uh, of the temperature star determines the peak wavelength. There's a relationship between the temperature of the star and the color. So for instance, this star will appear red. This star will appear blue because it gives off more energy in the blue part than the red part, and the sun will just appear basically white, right? Okay. So again, the relationship that we did previously is 3 times 10 to the 6 divided by T in nanometers. I don't know why I have 2.9 here. It's roughly 3. So hotter stars emit more energy per square meter on the surface, right? So basically, if we can measure the temperature of stars, right, then we can figure out basically um, how intrinsically bright they are, right? So the second fact we need is a way to find the size of the stars, and then basically we figure out the distance from that. Okay, so there's a relationship between colors and temperature, right? So basically, as they get hotter, so basically Betelgeuse is a very just a giant but cool star, so it's 3,000 degrees Kelvin. It appears red, and it gets hotter and hotter. So the sun is a nice yellow star. Okay, as it gets hotter and hotter, so Vega is a white star, whitish, really bluish, and then Rigel is a blue star, 20,000 degrees Celsius, and then basically there's some Mangati or Delta Orionis, which is at 30,000 degrees Kelvin, so that appears basically electric blue. So there's Betelgeuse there, being bright red. There's Rigel right there, being quite blue. Okay, and so this is just another relationship of that. The hotter the star, the, the shorter the frequency, shorter the wavelength emits, the higher the frequency it is. Okay, so we have to understand a little bit about stellar spectrum, right? So William Wilkinson and Joseph Fraunhofer in Bavaria, Germany, developed the spectroscope in the early 1800s, right? And so spectroscopes are basically telescopes with a prism associated with them. And so Wollaston was the first to see dark lines in the spectrum in the sun. And by 1863, right, as we talked about in light and matter, that these dark lines were identical to the patterns of spectral lines from particular elements found on Earth. So basically, they saw that these dark lines were essentially indications that these elements that are seen on Earth are also present in the sun. Okay, it happened to be the case that one set of lines failed to match the spectrum of any known element, right? And so the conclusion was that we're seeing an element on the sun that had not been seen on Earth. So it's given the name helium after the Greek god Helios, right? That's why helium's got named um, for it, so because of Helios. And later on, they discovered that helium was present in basically natural gas wells all over the place. And so basically, this first element that was seen outside of the outside of Earth before it was identified on Earth. Okay, so a great variety of stellar spectrum were observed for different stars, but the differences do not reflect any great difference in composition because basically they have all the same elements. So back around time, a Harvard astronomer called Edward Pickering started to create catalogs. That's what you do basically when you're doing astronomy a lot of times. You basically just create catalogs of these things, right? And initially he bought a bunch of male assistants because this is like around the turn of the 20th century, and so basically most jobs were filled by males, but he was frustrated with his male assistant and famously declared that his maid could do a better job, right? So he was right. He hired his maid, came Wilhelmina Fleming, and later a bunch of other women around 1881. Right. So there it is. There's Pickering, and there's his crew. Right. And they were known back then as the Harvard computers. So the first computers were women, and they developed a classification system for stars that we know today. Right. Now the most famous of them was a woman named Annie Jump Cannon. So Annie Jump Cannon, during early part of the century, I classified almost 200,000 stellar spectrum. So she consolidated early classification by William Pickering that had been arranged alphabetically according to the strength of the hydrogen absorption lines, right? So you look at the hydrogen absorption lines, and basically by looking at their strength, you basically say what this particular star is. So A was strongest, B weaker, down to P, right? There's Annie Jump Cannon, right? So she looked at a spectrum of 200,000 stars, right? That is a lot of stars, a lot of work, okay? So if you order stars from hottest coldest, you get basically order from hottest coldest. The spectral types are O, B, A, F, G, K, M, right? So basically this was initially A, B, C, D, right? But if you order them by temperature, it's O, B, A, G, O, B, A, F, G, km. The sun happens to be a G star. The mnemonic means O be a fine guy / girl, kiss me. All right. O are the hottest stars. They have temperatures greater than 25,000 degrees Kelvin. G stars like the sun have a surface temperature about 6,000 degrees Kelvin. And M stars are the coolest stars, right? Betelgeuse, for instance, with surface temperature approximately 3,000 degrees Kelvin. Okay. So why is it that you can that the temperature star changes the hydrogen lines that you see? Well, it turns out that as you increase the temperature star from 3,000 Kelvin to 10,000 Kelvin, a high percentage of the light excites hydrogen atoms, and the hydrogen lines get stronger, i.e., darker, right? But if that's true, why the hottest stars? Why is it OBA? Okay, why is it ABC? Well, it turns out that the hottest types, basically, the hydrogen has weaker lines because what happens is that hydrogen becomes ionized. So all the electrons in the hydrogen atom get knocked out around from the respective atoms. So there's just there are many fewer electrons to be excited in the first place, right? And so there are basically very few hydrogen lines in O stars, and like less hydrogen lines in B stars than say A stars, right? Okay. So great. So now you know the spectral type. You can identify them by looking at the spectrum of it. So basically you look at the spectrum, you look at how strong hydrogen line is, that gives you a spectral type. So now you know the temperature, right? So how do you know how bright they are? So there's a relationship between temperature and luminosity, and it's the following. It's basically L, which is luminosity, is 4 pi sigma. So pi is 3.14. Sigma is a Stefan Boltzmann constant. So these are some stupid constants here. There's the temperature. Temperatures go to the fourth power times the radius of the star. So how luminous something is depends on how big something is, and how bright something is. This is the brightness per unit area. Depends on the temperature. Okay, so you can figure out the size of the star if you know its luminosity and its temperature. Temperature you know because basically you know the spectral light O, B, A, F, G, K, M. Luminosity you know if you know the distance, right? So we have to return to this in a second. All right. So again, basically there are two ways stars can be bright. One is they can be really bright over a small area. So in order to do that, you have a very large temperature, or they can be very big, have very big R, or it can be both, have a high temperature and be very big. Though typically that doesn't happen. All right, so let's get some practice using this formula. All right. Okay. So how bright is a star that's 4 times larger but the same temperature? How bright is the star that's the same size but 2 times hotter? And suppose a star is 100 times larger but also 1,000 times brighter. What is its temperature? All right. So we need this piece of information. Sun shines at 1 solar luminosity. Sun is 1 solar radii. Temperature is 6,000 degrees Kelvin. Let's see. So let's just go back to here. Okay. So let's go use the video capture device and basically look at that problem. Okay. So first thing we know is that the sun shines with 1 solar luminosity. Okay. The sun is 1 solar radius. Okay, so this is solar luminosity. This is solar radius. Okay, it's good to measure things in terms of solar luminosity, solar radii. And temperature is 6,000 degrees Kelvin. All right. If you want, you can call this a solar temperature, but whatever. We'll call it 6,000 degrees Kelvin. We have a natural temperature scale already. Okay, so let's get that right. So L is equal to 4 pi sigma T to the 4th R squared. Okay, so we want to basically do this for the sun, right? So sun is going to be L is equal to 1 solar luminosity when the temperature is at 6,000 degrees Kelvin, the 4th power, and the radius of it is at 1 solar radii. 1 here, squared. Okay, so this is the formula that we shall use for everything below. So the first question, so how bright is a star that's 4 times larger? So R is equal to 4 solar radii, okay? But the same temperature. Temperature is equal to 6,000 degrees Kelvin. All right, so that's number one. Let's get that. L is equal to L solar T over 6,000 to the fourth R over 1 solar squared. Okay, let's plug everything in now. So this is L solar 6,000 degrees Kelvin, 6,000, right? So that goes up there. It's the fourth power. And now this one goes right here. 4 solar radii over 1 solar radii squared. Okay, and so this is 6,000 divided by 6,000, just 1. So this is L solar 1 squared, 1 to the fourth power. And this is 4. So 4 over, or 1 is 4. So our solar radii cancel out. Squared. So that's going to be equal to 1 to the fourth power is 1. 4 squared is 16. 16 L solar. Okay, very nice. Number 2. Okay, hopefully you guys are able to see the sheet as see the slide as well. If not, go ahead and print it out. How bright is a star that's same size but 2 times hotter? So R is equal to the same size. T is equal to 2 times hotter, so 2 times 6,000 degrees Kelvin, which is, we'll leave it like that. Okay, so then let's try the formula. L is equal to L solar T over 6,000, the fourth power, R over 1 solar to the square. So that's a 1 again. So L solar times 2 times 6,000 over 6,000 fourth, 1 solar over 1 solar squared. So that goes to 1. This goes to 2. So it's going to be L solar 2 to the fourth 1 squared. Okay, so that's 1 again. And then 2 to the fourth is basically 2 times 2 is 4, times 2 is 8, times 2 is 16. So again, 16 solar luminosities. Okay. Now let's look at the last one. Suppose a star is 100 times larger but also 1,000 times brighter. What is its temperature? So number 3 is basically so the star R is equal to 100 times solar radii, but L is equal to 1,000 L solar. Okay, and the one I don't know is R is equal to, sorry, I know R is, T is equal to question mark. Okay, so let's figure this one out. So write this one down. This L is equal to L solar T over 6,000 degrees Kelvin, fourth power, R over R1 solar squared. So we know this is 1,000. L solar is equal to L solar T over 6,000, the fourth, and this is 100 times larger, so it's 100 R solar over 1 R solar squared. Okay. So let's go figure this out. So it's going to be, let's write this thing out. So that's 10 to the 3. Okay, the L solars will cancel each other out. It's equal to T over 6,000 Kelvin to the fourth power. This cancels each other out. That's going to be 100 squared, which is, let's see, 10 to the 3 is equal to T over 6,000, the fourth power. That's 10 to the 4 now. Okay, so divide by 10 to the 4 on both sides. So that means that T over 6,000 the fourth power is 1 over 10 or 0.1. Okay, so I just tell you that this number is going to be pretty small. Let's see if I can think of what it is. It's actually square root. It's close to square root of 3. Um, but you can go ahead. I'll let you calculate this out. So T is equal to 6,000 times the fourth root of 0.1 Kelvin, right? And you can plug this into the calculator to figure out what this number has to be. All right, turn this off now. Let's go back to this next one and go. All right. All right, so now we're going to talk about the HR diagram, or the importance of making plots. So by 1910, one knew the surface temperature of stars and asked whether the surface temperatures were going to be related to brightness, right? So there are going to be two characters we're going to meet now, Edgar Hertzsprung and Henry Norris Russell, right? So in 1911, Hertzsprung looked at the spectra and the brightness of stars in a single cluster of stars. So there are stars that basically are together in giant cluster, but they could be up to basically 1,000,000 stars together. And he plot each star on a graph whose axis measures the brightness. Now the star cluster is basically all at one distance, so basically they're all, what you're measuring is that while you're measuring apparent brightness, you don't have to you don't have to worry about them at being different distances, right? And the temperature, the spectral class. And he found a remarkable pattern, right? Because all the stars cluster at the same distance, the difference in apparent brightness comes from difference in the real brightness or luminosity, the energy emitted per second. So in 1913, Russell made a similar plot for nearby stars whose distances were known by stellar parallax, and so whose luminosities were also known. Okay, so this is the differences between Hertzsprung and Russell. So Hertzsprung said everything was the same distance, right? So luminosity in this case is just proportional to apparent brightness if this is all the same. And what Russell did was that he knew what the luminosity was because he saw what the brightness, what apparent brightness is, and he knew what distances were because he knew distance from stellar parallax, the first measurement that we talked about. And then what they find, look at that. So this is a cluster. They all fit along basically a single line, a single track. Okay, all right. They're for two different clusters, right? Independent of the cluster, they seem to form the same track, and that's a good reason why. All right, so here's basically HR diagram for nearby stars, okay, and here HR diagram for brighter stars, okay, and this is spectral classification, so higher temperature to lower temperature, higher temperature, lower temperature, not so bright to much brighter, okay. So on the HR or Hertzsprung-Russell diagram, almost all stars lie along a curve called the main sequence. The hottest stars, also the most luminous stars, and the coolest stars are the dimmest stars. So the hotter star, the brighter it is in total luminosity. The smaller star, the dimmer it is. So 90% of all stars lie along main sequence, almost all of them below the sun, cooler and less luminous than the sun. All right, so most stars, basically, the sun's right here is a so-called average star, but about 90% of the stars, by number, basically lie below. So these are basically M dwarfs and whatnot. So there are two major surprises that come from finding temperature and luminosity of stars. So the first surprise, there are stars that are very dim, right? So luminosities, they're very dim, so luminosity is very small. So what does this mean, right? So because it's hotter, each square meter of the surface is bright, so it emits more energy per square meter of the sun's surface. But because the total energy of the star is very small, the star itself must be much smaller than the sun. So about 9% of these stars are very hot but very dim, and so they're called white dwarfs. White because they're hot, dwarfs because they're small. And these stars are really tiny. They're about the size of the Earth, not the size of the sun. So for instance, these are tiny, size of the Earth, about 100 times smaller than the sun. So this is A star, that's the sun, and that's a white dwarf. So they're hot, all right? They're hot, but not bright because they're so small. Second surprise, there's a small fraction of stars that have cool surfaces that are very luminous. So 1% of these stars are very luminous, but with cool surface, and called red giants. Red meaning cool, giant meaning large. So they're rare, right? They're not among the 50 closest stars, but there are a number of red giants visible in the night sky because they're so bright. And they're huge because they're 100 times larger than the sun in size. So for instance, this is 100 times larger than the sun. That's the sun of the red giant. That's the sun right now. Look at that, it's tiny. And so they're bright because they're so big. All right, so here you go. So there's the main sequence. There's the red giants. Some of these are called supergiants as well. All right, and then those are the white dwarfs. All right. So every star we know lives on the HR diagram. After all, stars have a temperature and luminosity. So understand how they live on the HR diagram will be a subject that we will study soon. All right. So as they move basically toward their left, they go to increasing temperature, and move to the right, they go toward decreasing temperature. So the HR diagram plots luminosity versus surface temperature, and 90% of stars lie in the main sequence. So the hottest stars in the main sequence are also the brightest star, and the dimmest are also the coolest. So that's a bit of a surprise. Okay. So once you know a star, and you kind of know that they live in the main sequence, and you know the spectral type, you also know how bright it is intrinsically. And so from that, you can start to use that to determine distance, right? So in astronomy, we have to basically measure distances, and there are distances for stars that are close. We have very precise measures. Stars that are far away, we have less precise measures. But everything bootstraps on each other. Okay. So in astronomy, we start one distance scales and build on that. So the first thing we know is the size of the Earth. From the size of the Earth, you can deduce the size of the Earth's orbit. From the size of Earth's orbit, you can get the distance near a star. And once you know this nearest star, the distance near a star, you can get the luminosity near stars. And once you know the luminosity near a star, you can associate with a stellar type, right? And so basically, you've realized that like you could figure out what the luminosity of the star based on its temperature. So if they sit in the main sequence, so main sequence in this way become what's called standard candles, right? Something of a known luminosity. And so once you know that your star is a particular kind of main sequence star, so type B for instance, you know its luminosity. So by measuring its apparent brightness, you now find the distance. So in fact, the luminosity distance relationship. So this allows you to find distance to stars throughout our galaxy. Right. So this is how it works. This is spectroscopic parallax, right? Not brightness parallax. It's spectroscopic because you need the spectrum to find what spectral type is. So first you measure brightness and you measure spectral type of a star. You could use spectral type to estimate luminosity, assuming it all lies in the main sequence, and then use inverse square law to determine distance to the star. Okay. So you study and classify the spectra near stars, then you see where stars fall in the HR diagram. So they fall around here. Okay, so you look at this spectra. This is a KV type supergiant star, KV type main sequence star, right? So for instance, like you could basically start measuring. So radar ranging measures distance about 1 AU. Stellar parallax measures distance up to 200 parsecs. Spectroscopic parallax can measure basically up to 10,000 parsecs, which is roughly the size of our galaxy, right? And if you keep going on, you can basically take this to the edge of the universe, right? So in 2011, Saul Perlmutter, Brian Schmidt, and Alan Rees won the Nobel Prize in Physics, basically for doing that, right? For measuring the distances to the most distant objects in the universe. Well, not most distant, but the distant object in the universe, right? So again, basically, I preface this section by saying the importance of making plots. Hertzsprung and Russell made a plot and discovered an important relationship. These guys essentially made a plot and also discovered an important relationship. So these three discovered something called dark energy by using the same form that we're encountering. We know luminosity, we know how bright it seems, and so we can measure distance, right? So you remember this, how bright something is. If you know how bright something is, you can tell how far away it is, but look how bright it seems, right? Okay. And so they use a special kind of supernova called type 1a, which they knew how to tell how luminous it was. So same as main sequence. For main sequence, you look at how what the spectral type is, and now for the spectral you can deduce what the luminosity is. For these types of supernova, you could look at some other quantity, namely the K rate, and you also tell how luminous they are. So then using the formula, you could basically they figured out that the universe was slightly bigger than what people expected, right? And or explain this larger size. So for instance, this larger size, they had to put basically 70% of the universe in a form known as dark energy, right? So that's how they discover dark energy. So essentially, this is the plot they use to essentially show that, right? Right. So we can also try to measure stellar masses, right? Um, so Herschel, starting 1782, looked for parallax by observing pairs that look close to it. He expected the stars would not really be close enough, but they were simply in the same direction, one star farther away than the other. And I hope you see the apparent motion of the nearest star due to the Earth's motion around the sun. Instead, what he found was the pair of stars were actually, in fact, close together, right? And the orbit at common center mass for periods of several years. So he found there are some 64,000 visual binaries. Herschel found 800 of them, and most of them have very long periods, greater than 1,000 years. But for some of the visual binaries that are close to each other, one can plot their orbits and see that these stars obey Newton's or Kepler's laws. So it turns out about half of all stars are in binary systems. The sun is unusual in that it doesn't have a companion. So a visual binary is a binary system whose stars can be distinguished with a telescope. But in many binary systems, stars are too close to be even told apart with a telescope. So even through a telescope, it looks like a single star. Close stars, however, move much more quickly, right, because of Kepler's laws. And so the spectral line of each star will be blue shift and then red shift on a periodic basis. So spectroscopic binaries are observed by looking for a periodic Doppler shift in the spectral line of each star. And so you can also tell stars if they are spectroscopic by looking at how the line shifts, or eclipsing if the star changes in brightness on a periodic basis. So here are some visual binaries, right? This is over a period of 48 to 83. It's about 40-ish years or so, right? You can see this is the star's position of the companion slowly changes over time. You want to tell spectroscopic boundaries. Basically, these stars have the orbit much closer to each other. And over a period of time, basically, if you look at the last spectrum frame, it first gets red shifted, moves to red, then it gets blue shifted at time t at a second time. And by measuring the shifts, the period in the shifts, you can measure how quickly these stars orbit each other. Okay. Finally, there's eclipsing binaries. So if the star's configuration is suitably favorable, the star will pass in the face of the other star. Okay. And so what happens if you measure the total intensity of stars? So there's two stars here, some brightness. Now you basically blots out part of light of the first star. It gets dimmer. Now you see two stars again, same brightness. Now the other star has gone behind it. You see a secondary, what's called secondary eclipse. You see it again, and then basically you see the primary eclipse. Okay, so these are eclipsing binaries. Basically, you see this. In some cases, you see basically the primary eclipse, secondary eclipse, primary eclipse, secondary eclipse. This is well, I think this one's supposed to be much brighter. Yes, this one's supposed to be much brighter than this one. Okay. So, for instance, Mizar is a system of 4 stars, right? Through a telescope, it looks like a visual binary, right? But each of these stars is really spectroscopic binary on its own, right? So basically, it was discovered by William Pickering in 1889, and the other was found basically as a spectroscopic binary in 1908. So this is Mizar. In fact, this is not 2 stars, 2 pairs of stars. The star Algol in the constellation Perseus is eclipsing by a period of 3 days or so. So you see basically over a period of 3 days, it changes its brightness. With precise measurements of its brightness, you could tell that's an eclipsing binary. And basically from this, if you look at the period and the orbit of each star, you can figure out the mass. So by looking at the speed of each star in the binary system, all right, by just spectroscopically, measured by looking at the Doppler shifts and then measuring the period of each star, you can tell basically how quickly they're orbiting each other and the distances between the stars. Okay, and so from that you could deduce the mass of the stars. One can understand the main sequence, right? So what determines where on the main sequence the star will be when it forms? So it turns out that stars in the main sequence are only distinguished by their mass. All right. So in fact, that HR diagram, that pattern that Hertzsprung and Russell found, the line of the stars that follow just follows the mass. Small mass stars are cooler and dimmer. More massive stars are hotter and brighter. Okay, so stars with small masses are low in the main sequence. They burn very slowly, they're dim, and the surfaces are cooler. Stars with much larger masses burn much more quickly and have hotter surface and also hotter interiors as well. So stars don't move along the main sequence. You cannot, the star does not move along here, right? They basically are born there and they stay there until they start dying. Then they move off the main sequence, right? So they sit on the main sequence until their time there is up. And basically the main sequence is a way station where stars spend most of their lives. So here's a summary. The difference between stars on the main sequence is due to differences in their mass. Low mass stars are low in the main sequence and are much dimmer. Our star 1/10 of solar mass may only be 1/1000th as bright as the sun. Similarly, high mass stars are high in main sequence and are much brighter. Our star of 10 solar masses might be as bright as 10,000 times brighter than the sun. So, how long does a star live? A star spends nearly all its life burning hydrogen and helium at its core. The time that it can do that is limited by how much hydrogen it has. So now we figure out basically how long it takes the stars to fuse the hydrogen to in its core to helium. All right, so let's basically review back how energy is produced in stars. So energy is produced in stars when you take 4 hydrogen atoms and produce 1 helium atom. And the difference between mass between 4 hydrogen atoms and 1 helium is a 0.7% of a hydrogen atom. And that 0.7% is converted to energy by E equals mc squared, right? So the person who measured these differences between the masses of hydrogen and helium was basically Astron in 1920. So he basically he used this as the setup he used, a bunch of magnets. He watched how things bend under a magnetic field, and that tells you the charges and the the masses of these objects. Okay, so again, we go back to Eddington again. Eddington basically guessed that basically 0.7% of this mass defect or mass difference basically changes to energy via E equals mc squared and powers the sun. So in order to figure out the lifetime of a star, there are 4 steps. You have to use the energy the star emits per second to find the mass the star changes the energy each second, and then find the amount of hydrogen that is consumed per second that this represents equals mc squared, right? The amount of hydrogen is basically 1 divided by 0.07 or 143 times the mass found number 1, and then from that you can get the lifetime, right? So there is a simpler way of doing this. We do know, however, that the lifetime of the sun is about 10 billion years. So from this, we can get the lifetime of other stars, right? So this is the mass of the core, and you say that the mass of the core scales the mass of the star. So the mass of the core in the sun is 1/10 the mass of the sun. And so basically for other stars, it might be 1/10 the mass of those stars. Okay. And the total amount of fuel consumed per second, well, that's related to the luminosity, right? So if it's 1,000 times brighter than the sun, then it consumes 1,000 times more fuel per second, right? So based on this, right, you can write down basically the following formula. The lifetime of a star is 10 billion years times the mass of the star in solar units divided by the luminosity of the star in solar units, right? So here's a simple example. A main sequence star has a mass of 5 solar masses and a luminosity of 1,000 solar luminosities. What is the star's lifetime? So let's do that calculation. 10 to 10 times 5 solar masses divided by 1,000 solar luminosities. That's basically 5 times 10 to the 7 years, or 50 million years. Okay, so let's go ahead and do some simple units, simple tests, simple examples. The lifetime of a star is equal to 10 to the 10 or 10 billion, times the mass of the star in solar units divided by the luminosity of the star in solar units as well. So we're going to do a star with 1 solar mass and 1 solar luminosity. What is its lifetime? A star with 10 solar masses and 10,000 solar luminosity. What is its lifetime? And a star with 4 solar masses and 200 solar luminosity. What is its lifetime? So let's go to, the video here. Okay, So let's write down that formula again. T life is equal to 10 to the 10 m in solar units divided by L in solar units years. Okay, so number one, we know the mass of the star is 1 solar mass. The luminosity of star is 1 solar luminosity. So these are in solar units. So T life is equal to 10 to the 10 m over L years. That's 10 to the 10. So m is 1 solar unit, L is 1 solar unit. So that's just 10 to the 10 years, right? And this makes sense, right? Because we knew that the lifetime of the sun is 10 billion years. So if a star shines exactly like the sun with the same mass as the sun, it's also going to live for 10 billion years. So number two, star has 20 solar masses. M is equal to 20 m solar, and L is equal to 10,000 L solar. So let's write that form again. T life is equal to 10 to the 10 m over L. That's 10 to the 10. 20 over 10,000. Okay, this is 10 to the 10. 2 times 10 to the 1. 10 to the 4. Okay, so this is going to be equal to 10 to the 10 times 2 times 10 to the 1 over 10 to the 4. So that's 10 to the 10 times 10 to the minus 3 times 2. All right? So this is going to be equal to 2 times 10 to the 7 years, right? Which is 20 million years. Number 3, okay? M is equal to 4 solar masses. L is equal to 200 solar masses. Let's do that again. So T life is equal to 10 to the 10. I'm not going to write the formula. I'm just going to write everything down. That's 4 divided by 200. That's 2 times 10 to the 8 years, right? Or 200 mega years or so. All right, so that's it for this lecture.